answers. So I'm trying to keep it as collaborative as possible here towards the end, but when I ask you to stop talking, please stop talking to your group, vice versa. If I'm ready for you to go for it. But let's go answer some of these warm-up questions, kind of recap some of the heat things and the terminology specifically that we learned in our web quest. It was a very, very inclusive web quest, so I feel like you have a lot of background knowledge right now, so I'm trying to pull it back out of you, okay? What happens to an ice cube when it's added to a soft drink? Brandon, tell me about it. Use your words. I know, sorry, are you eating? Okay, let's go. Scott, go for it. Spoon in mouth. Uh-huh. So it's warming up because of the difference in temperature. So when does it stop warming up? What's that term called? Thermal equilibrium. Thermal equilibrium is when it's going to stop now. That's going to be a little bit further down. Number 2, what is the rule about how energy is transferred between two objects that are in contact? Flows from what to what, Kyle?
Flows from higher temperature to lower temperature.
Right, and we try not to say hot and cold because cold doesn't apparently exist, so it's just high amounts of energy to lower amounts of energy. True or false? Explain. All particles of a substance have the same kinetic energy. True or false? Okay, so it's false because what's technically true? What can you adjust to make that a true statement? Scott. Okay, some particles have the same kinetic energy, or even we can go further, particles of the same temperature have the same average kinetic energy. The average might be a constant, but it's going to be more about each individual particle can be faster or slower than others, having more heat than others, more temperature, more energy than others. So it's more about the distribution of energies, not like they have the same energy. And there's a little distribution curve. What does it look like on your sheet? That talks about the relative energies that they have associated with them. You see this little curve that looks like this? It's like a bell curve. Okay, some of them are fast over here, some of them are slow over here, some of them are average in the middle. So that's helping you to see that that's not a true statement. Number 4, what is the definition of temperature? Trinity, definition of temperature. Okay, Morgan, what you got? Okay, so the amount of movement. There's a term that goes along with movement. Collisions occur because of this. Yeah? No? Kinetic energy. So we're going to actually use that term kinetic energy quite a bit. The definition of temperature, and this is on our notes for today, so write it down now, so we're not going to write it down later. It's the average kinetic energy of the molecules. Or the temperature is equal to the average kinetic energy of the molecules. So that's a really important definition because it's helping you to see that temperature and energy, or temperature specifically molecular kinetic energy, is going to be highly, highly associated. Hotter things move faster. And I think we all kind of knew that already. Like, it feels like that's common sense. Hotter things move faster. Yeah, that's why steam comes off the top of a spoon and then you can blow it away so that your soup cools down. All right, describe the collisions, the results of collisions between faster moving particles and slower moving particles. So the faster moving collisions, are they going to be of higher impact or lower impact? Higher. Again, common sense. Slower moving particles have a lower impact. So there's going to be something related to activation energy later on when we talk about the collision theory in reference to that question. Let's go to, we did talk about 9 last week a little bit. So let me go there real fast. I saw a couple of you guys drawing this already. What does a heat curve look like? Like stairs. So does it start flat or does it start at a slant? Slant. Slant first, then flat. Slant first, then flat again. Slant. So at this part here, here, and here, what is happening? Specifically with temperatures. Temperature changing or is temperature staying constant? Temperature is changing because this is the temperature axis. So if temperature is changing here, and we want to find the heat associated with this. This is what was in the web quest. How do you calculate heat when the temperature is changing? What formula do you use? MCAT. Q equals MCAT. MC delta T. The delta looks like an A. That's why we say MCAT. So that's going to be true for 1, 2, and 3. There's 3 slants where the temperature isn't being changed. But then we have a situation where we don't have temperature changes. What's happening at these green sections here? What's happening? I heard phase change. Okay, so there's a couple things. There's a couple of terms you can use here. Phase change, and I also heard physical equilibrium. It's just when you're going from liquid to, or in this case, solid to liquid, liquid to solid. It's just at this equilibrium. This is a double-headed arrow, if you can't tell. Double-headed arrow. And since there's no temperature change, we cannot use MCAP because it has a delta T in it, and we don't have one. So what equation are you using here? Q is equals to moles times delta H, and delta H is different between the first phase change and the second phase change. The first one is called what? I know it's called melting, but what's the delta H associated with that? Delta H blank. Fusion, delta H of fusion. So here's what I'm saying. Delta H fuzz, which is fusion. Fusion is another name for melting. And what's the second delta H called up here? Vap, right. Delta H vap, which is vaporization, which is the phase change of liquid going to gas. So a lot of this, some of this is review because we learned a little bit about it in chapter 13 with phase changes. So let's stop on that for a minute. Let's go to foldable. Everybody has their basic construction done? Possibly? Basic construction. So what I'd like to do is I'm trying to keep you organized, first of all. And a lot of people with a gas foldable said that it helped you a lot. So I wanted to try this again. So going through the first part of this. We already talked about this, and the heat definition you have on your reading guide. Reading guide, do you have this in front of you? You have this definition. I'm not going over definitions because definitions is just me reading off the board, and that's really boring. So there is a difference though between heat and temperature. That's really what I need you to know. Heat is more of a summation of every single energy type possible in the sample, where temperature is just an average of the kinetic energy of the sample. So there's two different definitions, but they are two different things. How do we denote heat? What variable do we use to denote heat? Q, okay? So this is Q, and temperature is T. Now what you're going to see is with gases, we had to use Kelvin every single time with temperature. With thermochemistry, we don't necessarily have to use Kelvin. A lot of times it's going to be in degrees C, because a lot of times we're using thermometers to measure these temperature changes. So that's going to be a little different for us this go around. But before we move on, I'm going to skip this video for now. Let's actually set up our foldable. So these are the two equations we're going to be implementing. And what you can do is just put one on each of the flaps. There's 4 flaps, and if you don't have it exactly set up the way I've asked for you to, no big deal. I just need 4 sections in general. So the 4 flaps are going to be related to, first of all, Q equals impact, which is when temperature is changing. Q equals moles times delta H of fusion, or vaporization. That's only for phase change. And then I specifically want to talk about this one today, which is referencing the difference of energy exchange between a system and the surroundings, or the surroundings and the system. Thank you. So, and at the very end, maybe tomorrow we'll actually get to the thermochemical equations. So under each section, you guys have these instructions on your sheet. Does everybody have that sheet in front of them? Yes? You have the paper I give you with these instructions on them? That's your paper. Please take it, okay? That has lecture problems on it that we're going to be doing today. That has foldable instructions. That has PS17, so you don't have to print it. And then something we'll probably do tomorrow, which is our thermochemical equations. So if you, and I'll try to pause and let you guys do this each as we go, but you're going to have a description or a scenario that would be occurring in the problem. So that would kind of trigger you to go, oh, I need to use this equation because this is what's happening in the lab scenario or in the problem. Definitions, if appropriate, that's probably going to be more about variables and units though, and then a picture or a diagram. So let's kind of start this together. Q equals impact. Can we start that section? Is everybody ready-ish? Okay, ready-ish. This is on your sheet. You don't need me. This is on your sheet, all of that. Okay, this is the big slide. That right there, number 1, is what you would be putting underneath the flat for Q equals impact. And it's telling you when you're going to be using Q equals impact. So this is like the scenario. You calculate heat when the heat is not being transferred from one substance to another. It's just the heat inherent. So it's like the internal heat of a sample. And I'm going to show you a video with heat transfer in just a second. So in this case here, this might be whenever you just have a metal and you want to figure out if the temperature has changed in that metal. Maybe it's been heated up somehow. When you have a temperature change, what is maybe the specific heat of the metal? What is the actual Q, the heat associated with that temperature change? They'll ask you about one of these variables, but usually not all of them. So Q again means heat. And what is the unit for heat? You wrote this down in your web quest. Joules or kilojoules, but generally it's going to be in joules. So I'm kind of defining some variables here for you. You can also put this under the flap and the foldable. M is mass, and that's generally going to be in grams for that sample. So I might say you have 5 grams of aluminum metal. You have 150 milliliters of water. Don't forget that if you're talking milliliters for water specifically, this is equivalent to the number of grams as well, because the density of water is 1 gram per milliliter. That's only for water, though. And then C is specific heat capacity. What are the units for specific heat capacity? Look at your web quest. Joules per gram degrees Celsius, right. It is a big unit like our R unit back in gas laws, but it does require you to write it every single time, and I want to show you how they cancel out in just a second. And then, so since our C, our specific heat capacity, has a delta or has a degree C in it for Celsius, our temperature change in this case will be expressed in degrees Celsius. But how do you calculate temperature change? What was the general format for that in your web quest? That how do you check? Which one goes first when you subtract? Right, T2 minus T1 or T final minus T initial to give you your delta T. So here is what we will generally set up. So sometimes you'll have a negative delta T, but if the temperature has maybe cooled down, because the temperature final will be lower than the other. So before I move on to another type, I want to do an example problem with this. You guys have those example problems in front of you, so you might want to actually start a sheet of paper for like example problems. I don't know that you're going to have room in your foldable. You can try. It's up to you. I'm starting number 1 under 17, chapter 17, lecture practices. Ready? Calculators? Calculators, activate. Anyone, Allison, going to have one right here? I don't have them out. So I'll probably do 1 or 2 examples with each type. All right, so this is our first example problem. Let's read. You can come in front, okay. Come across. Let's read and write down our givens first, and then we'll go. Because with these equations, sometimes you are definitely going to need to figure out which one you're solving for before you move on. Just like with our gas laws, we try to write down our givens. And this is how I've always been successful, so that's why I'm trying to pass on the skill sets on to you guys. So a piece of stainless steel weighing 1.55 grams. What is that? Mass. Okay, so I don't even know what equation I'm using yet. I'm going to write down my givens, and then the equation will jump out at me, okay? So mass, 1.55 grams. And it absorbs 141 joules of heat. What is that? So we already got this taken care of. What is this? This is heat, which is Q, right? So Q is 141 joules. And it says it's absorbing. So give me a quick...
Attention all staff, please take an email that was just sent by Mr. Lowry about a revised lunch schedule for today. Thank you.
Hold up, people. Hold on. Just calm down. Calm down. What? You have lunch in 6 minutes. Teal A, which is science, you have lunch from 10:55 to 11:20. I don't know. No teal. What? I don't know. Maybe something, I don't know. I can't postulate anything. You guys have lunch in 5 minutes. Let's finish this question. All right, with me. I have you for 6 more minutes. Silencio. What is absorbing? Endothermic or exothermic? Endothermic. And if this is endothermic, then that means heat is being absorbed into the metal sample. With me? You guys with me? I'm asking this table. Okay. So when the temperature is increased by this, so what does that give us? So delta T is 178 degrees C. Do not convert it to Kelvin. It is good as is. Question is, what is the specific heat capacity? Sorry, it's cut off. The specific heat capacity of the metal. So what are we looking for? What variables? C. We're looking for C. So I need you to quickly set up Q equals MCAT, isolate C, the variable C, and then let's plug and chug, okay? Because that's all this is. Once you got everything written out, it should be easy peasy. Q equals MCAT. Divide by what? Divide by M. Delta T, so I call that MAP, okay? So dissolve. Divide by MAP, okay? So this cancels. C is equal to Q over M delta T. And that's what you guys actually, some of you guys wrote on your reading guide, because I think that's how they set it up in the textbook. So let's plug. What's Q going, what is the Q going in here? 141 joules. Write those units, people. No mercy on this unit, okay? And gases, you're a little bit slacking. You should have your units on everything. M is 1.55 grams, and delta T is 178 degrees C. Guess what the units that are left over, guys? Does anything cancel?
Nothing can.
Nothing cancels, so guess what it is? Joules per gram degree Celsius. Okay, so plug that in. Please put that in your calculator correctly. .51. Okay. Can I get a second? 0.51? Yes? Okay. Before you go, let's look at this real fast. This is the C for a metal. Note to self, C's of metals are usually really low. Usually less than 1. Don't be scared if you get a 0.1, 0.2, 0.3, 0.4, right? So for metals, they're generally very low.
Teacher, please pardon the interruption.
For water.
To reiterate what Mr. Lowry said, please check your emails.
Make sure nothing
There's
changed.
been a schedule change for today, and a lunch will start when the bell rings at 10:55.
I got
Thank
2
you.
minutes, okay? So, yeah. Duh. Yes, it's like normal. You have luncheons at 12:45, so. No, I said no teal time. Sorry, no teal. I was very upset. I meant lunch day. I meant lunch day. Okay, backtrack. With me? Yeah. Okay. Metals are very low in their specific heat. Water has a special specific heat. What is it? 4.18 joules per gram degree C. Huge, okay? So let's talk about what this means before we move on. This right here means water will have to absorb lots of heat before it increases in temperature. That's what that means. So water, you have to heat it and heat it and heat it and heat it, and then finally the temperature starts to change. That's great, because in the summertime, in March, is it nice to swim in the ocean? No, it's really cold. When's a good time? Okay. So July, it's been warming up since May, June, July. How about October? Is it still nice? It's actually retains its heat pretty dang well, because it's not going to lose it like that. It's going to take a while for it to lose it's going to take a while for it to lose its heat, which would then cause the temperature to drop. Metals, on the other hand, you set it on the stove, that baby heats up so fast, and you put it on the counter, it's going to cool down relatively fast too, at least compared to water, because water has a large number of joules it has to absorb or release before the temperature will change by even 1 degree Celsius. Metals, on the other hand, can absorb half a joule, and it'll increase in 1 degree Celsius, versus this needs 4 joules to increase by 1 degree Celsius. So that's what that term, that specific heat capacity should really tell you. When you get back, we are going to do Q equals Q and the rest of mine. I'll see you in 25.
Really? 30 minutes?
I'll see you at 11:20. 11:20. This is weird. Record. Okay, so I'm not down here. Okay, so this is the study that involves heat transfer, and usually it uses something called a calorimeter. What is a calorimeter? It was on your reading guide. Jordan, Shayna, can you guys grab a calorimeter, a coffee cup calorimeter? I think they're underneath that cabinet. You know, the microscopes, behind the microscopes, down there. So a calorimeter is a device that usually is going to be able to maintain a certain temperature. And Jordan's going to hold up a really fancy one. I know, you're in awe. Just wait for it. Here it is, guys. It is an insulator. We put hot stuff inside, and you can't feel it on the outside. This is a calorimeter. We use the cheap one called coffee cup calorimeters. There are also ones called bomb calorimeters. And the bomb calorimeters are usually metallic. They're metals, and they do have many explosions that go on the inside. And they're metals, meaning they're not going to, hopefully there's no shrapnel going everywhere. This would not contain the explosion. But that's basically bomb calorimeters. That's how they determine the calories in all of our food. They just blow up food inside the bomb calorimeter, and they detect how much heat transfer is occurring. And they take the heat transfer, which is in joules, and they calculate it, or they convert it to calories. They pop those calories in the back of your nutrition labels. That's it. Who wants to be a nutritionist now? Okay, the calorimeter kind, not just like, okay, you should change your diet. Okay. So, you are going to be talking about how the heat is transferred between two systems. But usually one is hot, one is not as hot, and that transfer is going to occur. So the heat that's lost by one, we are going to record that as a negative value. The negative value is meaning that it's exothermic, that's transferring heat out of it. And if it's gained by the other, let's say it's lost by one, gained by the other, this one's going to get a positive sign for the heat because it's gaining. So they both can't be positive, they both can't be negative. Then one of them must be positive, one of them must be negative because it's referring to the heat transfer. So I don't have those signs here, but we will in a second. So let's watch the video first. And actually, here's what ours will look like. Who goes there? Hey, Viviana. Is that for me? Oh, more stuff for me. How much do you got? I'm going to scrap that one too. Okay, thank you. So here's what ours will look like. We'll put a thermometer in it. We'll have usually two balls, two styrofoam cups together, and we'll have a reaction going on the inside. So that's what ours will look like. Let's watch this video first. This is not the video. Oh, hold on. Let me stop this music first.
So I talked a little bit about this idea of enthalpy. That enthalpy will allow us to establish whether or not a reaction is exothermic, that is giving off energy to the surroundings, or endothermic, that is taking energy from the surroundings.
Write down exothermic and endothermic someplace. We have talked about it before, but it's going to kind of start coming back into play. So let me rewind him for just a second.
This idea of enthalpy. The enthalpy will allow us to establish whether or not a reaction is exothermic, that is giving off energy to the surroundings, or endothermic, that is taking energy from the surroundings. And you might be asking, well, is there a way that we can easily perform a reaction and figure out whether or not it's exothermic or endothermic, and maybe even measure to what degree or what the magnitude is of the exothermic nature of the reaction or the endothermic nature of the reaction? And in a high school chemistry lab, this would be possible if we could find something that was readily available, cheap, and a good insulator. Styrofoam coffee cup, you say? Yeah, that just might work. In fact, we refer to this as coffee cup or constant pressure calorimetry. And the way that it works is that we perform a reaction inside this coffee cup in a solution. And the solution, the solvent in the solution is water. And since we know a lot about water in terms of how it behaves in response to energy transfer, we can then figure out, based on what happens to the water, whether or not the reaction is exothermic or endothermic. So we're going to use water, which we treat as the surroundings, to establish the enthalpy change of the system. So whatever energy transfer is from the reaction of the system into the water, that's going to allow us to figure out whether it's exothermic or endothermic.
So let's say we drop a piece of hot metal into, so there's water in here, okay? Water's inside the coffee cup calorimeter. You drop a piece of hot metal in. The hot metal is the system. You drop the hot metal in. What's going to happen to the temperature of the water most likely? Okay, it's going to go up. So what you're saying is the surroundings temperature, the water's temperature goes up. What's likely to happen to the temperature of the metal? It's probably going to go down because heat flows from hot to warm to less warm, or high energy to low energy. So the system is the hot metal, the surroundings is the water. That's the difference, and there's always an interplay and exchange of temperature or of heat between these two.
If the temperature of the water goes up, then the reaction must have released energy. If the temperature of the water goes down, then the reaction must have absorbed energy. Now, there are a series of calculations that we go through in order to establish the magnitude of this reaction in its endothermic or exothermic nature. The first thing we're going to take a look at is what this coffee cup really sort of looks like. And really, it's just that, a coffee cup. And we have a lid to try and make as close to a closed system as we can. And then we're going to fill it up with water. And what the water is going to give us is going to allow us to determine the energy transfer to or from the water if we can measure a couple of things about this water. And the relationship that we use, or the equation that we use, is Q equals mc delta T. Now, the mass is the mass of the water. It's important to note that it's the mass of the water because we're figuring out the Q of the water and not the mass of the reactants. So it's the mass of the water. And most of the time, we're going to be adding water in terms of a volume, that is, the number of milliliters that we put in. But since we need the mass, we have to remember that water's density is equal to 1 gram per milliliter. So if we put in 100 milliliters of water, it's going to have a mass of 100 grams. We're also going to use the specific heat capacity of the water to help us in this calculation. And we're going to remember, we're going to use it enough that you're going to remember or get to learn that the specific heat capacity of water is 4.184 joules per gram degree Celsius. But of course, this is a value that you can always look up. Now, in order to use these two values, we have to make the assumption that the solution is dilute enough to effectively have the properties of water. And in most cases, that's a pretty safe assumption to make. We're then going to perform the reaction and measure the temperature change of the water. And so this is where our delta T comes in. Delta refers to a change in, and T refers to the temperature. So our delta T here is the change in the temperature of the water. If the temperature of the water goes up, it's going to be a positive delta T. If the temperature of the water goes down, it's going to, of course, be a negative delta T. Enthalpy change of the reactant.
Okay, I'm going to stop there for a second because he's going to get into some more stoichiometry, which we're not interested in just yet. So let's look at the next question regarding calorimetry. You guys see this on your paper? This is the first one of 1 through 5. To my, let me see. It's like if you're noticing now, the very first section under the chapter 17 lecture notes and practice, that's regarding heaters and CAT mainly. And note to self, on 1 through 4 there, you might look at the specific heat values for some of these in your textbook, or you can Google them, but I'll tell you which one specifically to do. So we're going to work with number 1 first. So whenever you're setting up these types of problems, you are going to want to organize data very specifically. So here is generally how I set this up. Right, what is the specific heat of, okay, so what's our question? What value? C, we're looking for C, okay? So generally the system is usually, or the surroundings are usually water, and the system is usually metal. So I'll usually set up a quick table of Q, M, C, and delta T, and we're going to fill in the blanks for each of these. It really, really helps you stay organized. Something like this. Doesn't have to be perfect, but a quick table is an easy setup. So what is the C, the specific heat of blah, blah, blah metal? So the question is actually about the metal. So I'm going to put a question mark under C for that. And what else do we know about the metal right now? We know its mass. We know that it's 50.00 grams. That raises 100 milliliters of water. Okay, what does that tell us? 100 grams of water. Oops, I'm sorry, guys. I put that under Q by accident. That's under mass. And actually, the Q's here are equal to each other. So just put a big equal mark between the two Q's because it's Q equals Q because heat transfer is the same. It's conserved because of the law of conservation of energy. So that's 50 grams here. And you guys told me water, that's 100 grams because 100 milliliters is 100 grams of water. And it says the water in the calorimeter is raised from 34 to 36. So how do we find the temperature change of water here? So T final minus T initial, so you're doing 36 minus 34, right? So that's 2 degrees C. So this is going where? delta T for the water. Okay, so the water is increasing. We're going to need some Miss G needs them. So the initial temperature of the metal, initial Ti for metal, is 95. The final temperature of the water and the metal both always come to thermal equilibrium. So if sometimes you're having a hard time figuring out what the T final is for both of them, if you find it for one, you automatically have it for the other, and that's because it's undergoing thermal equilibrium. They always stop at the same temperature. So how do you figure out the temperature change for the metal? Well, you gotta do T final minus T initial, okay? So T final minus T initial would be 36 minus 75, negative 59 degrees C. So what does that negative refer to again for the metal? That it lost heat. It's exothermic in that process. So negative 59 goes over here for the metal. Okay, what else do we know but it's not on the table right now? We know the specific heat of water is what? 4.18 joules per gram degree C. Okay, so we know everything except for the C that we're looking for. So here's how we always set this up. And you guys actually did one of these on your web quest. So I hope this rings a bell for you. What happens here is Q of the metal is equal to Q of the water. Who's losing energy? The metal. So the metal gets the negative Q. Because you told me it's losing energy. It's transferring energy out of itself into the water. The water gets the positive value. So that negative is going to be carried along with us the entire time. So instead of saying Q equal to Q, because nobody even knows what Q is, we have to implement the replacement of Q, which is MCAT. So you get negative MC delta T for the metal is equal to positive MC delta T for the water. Now we're getting there, okay? So which variable are we looking for again? C of the metal. So this guy right here. Ooh, my board is so not aligned. We're looking for that blob right there, okay, guys? So let's figure out, how do I want to isolate blob? Divide by negative mat, right? Negative M delta T. Negative M delta T. Okay, so the negatives cancel, the M's cancel, and the delta T cancels, leaving us with the C of the metal. Now we're in business. C of the metal is equal to all this crap over here. Look at that. MC delta T over negative M delta T. Now it's very helpful that this is organized because ain't nobody got time to go back and read that problem again. Okay, so mass of water, go. 100 grams, okay. The C for metal, or for water. 4.18 joules per gram degree C. Keep going, delta T for water. 2 degrees Celsius. All of that over, so you guys see I'm just plugging in for MC and delta T for water. Now I'm dividing by, all of this information down here was for metal, and usually I like to label with M. That's just for your convenience. So negative 50 grams for the metal, and there we go. So that negative has to come back into place someplace, because you're going to see I have a negative in the degrees Celsius and a negative out here just hanging out. So what do those negatives do? Cancel, leaving us with a positive value overall for the C. So go ahead and calculate that. You got to practice this because some of you guys have set up everything right, but then didn't plug in your calculator right. So make sure you're comfortable with that. But there's a lot of numerator denominator business going on here. Well, you guys do that for a second. Answer? C of metal? 0.2834. Cool. Okay, I'm going to keep going until you tell me how many sig figs I need. So I think that was 2.0. So 2 sig figs, so this should be 0.28. And then units that are remaining? Good, joules per gram degree C. And I know that you know the specific heat capacity units are joules per gram degree C, but you can also verify that because the grams here and here cancel, the temperature change here and here cancels, And the only thing left is joules per gram degree C. Okay? So those calorimetry ones do require you to set up a little bit of information up first. I think this is helpful. And then Q is equal to Q because there's an energy transfer and it's 100% conserved. Are we okay with that one? This is kind of the second time we've seen this. Can I go into another example? Shake your heads, people. Okay, I need some of this. So the last thing we're going to do right now is possibly this information here. So go ahead, and this information goes under the fusion or the delta H fusion vaporization. That goes with this. Yeah, Q equals equal to moles times delta H. And the values for the delta H, how is this still not aligned? The values for the delta H of fusion vaporization for things other than water, we're going to use water a lot, but if you need anything else, they're on page 522 in your book. And I'll go ahead and tell you the values for water, just so you can have them for your reference. The delta H of fusion for water, you guys actually did write this down in your foldable. Does any of you remember it? Or if you, say it again? Say it one more time. Oh, you did joules per, okay. The joules per, is that joules per gram? Okay, I like that you said that because there's a reference sheet. Guys, it's still not aligned. Now it's just lower than it was. I'm really not liking this. Okay, there are two things to know. For water, the delta H of fusion in moles is 6.01 kilojoules per mole. That's one of them, and this is the one I'll commonly use with this equation because it has moles, so I need the unit with moles as well, so they cancel. On your reference sheet, you're going to get one that's a little different. It's 334 joules per gram of water. Notice that this one allows you to implement a slightly different equation because this one I use moles, so I'm requiring moles times delta H fusion. This one would be Q is equal to grams, or mass, right? Mass times delta H of fusion, as long as you're using this equation, joules per gram. This is the way I will probably most commonly do it, but you do have this successful on a reference sheet for the end of the year for yourself. So that's the delta H of fusion. Not a big number, 6 kilojoules, great? So delta H of vaporization, do you think it's going to be greater or lesser than the 6 number here? Why greater? Because it takes more energy to evaporate, to boil. Okay, so we're going from solid, in fusion, we're going from solid to liquid. And that's just like, okay, great. You've overcome a couple of intermolecular forces, not a big deal. Then you're going in vaporization from liquid to gas. So it's like huge difference in energy because you have to like literally rip all those intermolecular forces apart. It's going to be a bigger number, aka 40.1-ish kilojoules per mole. And I don't know the gram one off the top of my head, but this is only for water. And this is the one that we'll be using most commonly. So if I'm talking about delta H of fusion going from solid to liquid, that's a positive energy because that takes some energy to do. What would you think would be the delta H of freezing? Would that be a positive value or a negative value? Delta H of fusion means to melt. So we're going from solid to liquid. What if we go backwards from liquid to solid? Is that going to release energy or absorb energy? Release energy, and that would just change the sign to a negative value. Same story here. This being positive, going from liquid to gas. If we're going from gas to liquid through condensation, that would be a negative value for the 40 here. So we're working on the last section now, under your guys' homework or under the lecture notes. Oh, not that one. I'll come back to number 2. Okay, so this one, I do ask for you to draw a heat curve because it's going to be helpful to organize your thoughts. So I already have one drawn here, so you might want to sketch this someplace similar on your work that you've been working through right now. So the question is, how many grams of water at 100 degrees C and 1.3 could be vaporized by the addition of 180 kilojoules of heat? So if this one, that's not the one I'm doing. I'm doing this one. I'm starting on number 3. So starting on number 3, and I'll backtrack to number 1. All right, so as you read the question, how much heat? What unit is it, or what variable is it looking for? So Q or joules, right? So how much heat? So that's going to be annoying. Okay, so we're looking for joules or kilojoules, but it's just our unit for heat. We're on number 3 of the last section of the heat of phase change. Is required to change 52 grams of ice. Ooh, we got ice here, right? Okay, so that's important because ice is going to start down here at the solid phase at negative 15 degrees C to steam at 230 degrees C. So we are traveling the entire gamut here. We're going from negative 15 degrees C down here all the way up to 230 degrees C. You ready? This is going to be a trek that we'll take together. I need to figure out how much heat is required to get from every step of the way. So how many Qs am I going to have? And then at the end, I'm going to have to sum them all together. But how many Qs am I going to have initially? A little bit more. So this will be 1 Q, 2 Qs, 3 Qs, 4 Qs, 5 Qs, because each of these has a different equation that's associated with it, different mass, different temperature, and such. So the very first one, what is my stopping point right here? Sorry, my board is now really unaligned. What's my stopping point here at B? What's that temperature? This is water, okay? 0 degrees Celsius. Okay, what's the temperature here at D? 100. And how do we know these values? This is when it freezes or melts, and this is when it boils or evaporates, right? So we got to figure out this individually. Here we go. A little bit. Ooh, crayon. No crayons today. Okay. So Q1 is what I'm going to call this right here. What equation do I use when the temperature is changing, as you can see here? What equation do you use for when temperature is changing? Q equals MCAT, right? Oh, sorry, I already got Q there. Q equals MCAT. So let's figure out each of these things. What's the mass associated with this? Read the question again if you need to. 52.9 grams. What is the specific heat of ice? You want to write these values down because you probably don't have a reference sheet. But this blue reference sheet has like variables and constants on it. So I'll go ahead and tell you the specific heat capacity of ice is 2.05. Okay, so ice is 2.05 joules per gram degree C. And for liquid water, we already know is 4.81 grams joules per gram degree C. And for steam is 2.02 joules per gram degree C. So we're going to use those C values separately in a second. So this C value here is 2.05 joules per gram degree C. What is the temperature change associated with this first step? 15, because you're doing 0 minus a minus 15. So 0 minus a minus 15 is just a positive 15. Okay, please make sure you're working through this example with me, because this is the only one I'm going to do of this type. Okay, so go ahead and calculate your Q1. Calculate. Anybody? It is a big number, yep.
1,626.9.
0.7. And this is in joules because what you'll see is that grams on top and bottom cancel, and then I know this temperature could be up here, but C and C cancel, so joules is the only unit left. So Q1 is 1626.7 joules. Okay, let's do Q2. Q2 is going to be this change right here. What equation goes with phase change, meaning no temperature change? Q equals moles times delta H. So I'm going to just keep working down my board. You guys have a lot more space than I do. So Q is equals to moles times delta H of fusion in this case because I'm melting the substance. So what do I first need to do here? I got 52.9 grams. Stop. What do I need to do first? Go to moles, right? So I'm just going to kind of do this within the problem if that's okay. So Q2 is equal to 52.9 grams of water. What's the molar mass of water? Molar mass of water. 18.02. So it's hydrogen plus oxygen. 18.02. So I'm just doing that, and if I put that in parentheses, to me that means I've got moles. I'm not even going to finish calculating it right now. I'm leaving it as is. And then what's the delta H of fusion? I just told you for this problem you read it just previously. Delta H of fusion. Look in your folder map. What is it? 6.01 kilojoules per mole. So what units cancel here? Moles. So grams cancel, moles cancel, kilojoules is my remaining unit. Go ahead and calculate how many kilojoules that is, guys. Remain active with me. Calculation. Anybody? 17.6, and that's kilojoules here, okay? Circling, highlighting, whatever you're doing is going to be important because you're going to have a lot of work and you're going to want to find each of your Q's. This is in joules, this is in kilojoules, though, so just keep that in mind. Okay, guys, halfway there. Mostly. So we've now traveled from the solid phase, undergone phase change. Now let's figure out how much heat's associated with the liquid phase to get it up to temperature. What equation do I need to implement here? Q equals MCAT again. So I'm going to keep walking you through this, but I'm going to go a little faster this time. So this is Q3, which is Q equals MCAT because there's a temperature change. What is that temperature change? 100, right? I'm going from 100 back down to 0. 100 minus 0 is 100. So Q equals MCAT is what I heard. So let's go. Okay. Q3 is MCAT again. And Q3 is mass is still the same, 52.9 grams. What's a C for water liquid? 4.18 joules per gram degree C. And what was the temperature change here? 100 degrees C. Okay, calculate. Now, go for it. You guys can't get sleepy. I gave you pudding. Okay. Keep your hand in the game. Okay, anybody else get 20? Don't be scared of these numbers, people. 22,112.2 units. Now, is this what you got?
Yeah.
Okay, we stopped waiting. It's all good. All right, be ready. Q4. I'm trying to color code for you guys, okay? Q4 is my next step here. What is associated with that? I hear HVAP and I hear moles times delta H because there is no temperature change, so I can't use anything with delta T in it. So our number 2 and 4 will look very similar, but the value for delta blah will be different. So Q4 equals moles times delta H VAP. Moles, we just calculated that. Did anybody actually calculate the moles? Thank you. 2.9256. Okay, this is how many moles of water that 52.9 grams correlates to. And delta H VAP was 40.1 kilojoules per mole, as I told you for your foldable. Moles cancel, boom, boom. And ready for a calculation? Paige, what you got? Yeah.
117.317.
That's good. 3-1. Got it. Kilojoules though again, right? So this is in kilojoules, this is in joules, this is in kilojoules, first one's in joules. Okay. Am I going too fast? Are you picking up? I'm putting down. Some of us are not, but we will get there. All right, Q5. Which equation do I use for Q5, which is going to finally get me to 230 MCAT again? So I've got to get all the way up this track here, and that's going to be a Q5 because I'm going to start at 100 and get up to 230. So what is the temperature change there? Everybody see we're going from 230 down to 100, so that's 130 degrees change. So Q5 is equal to MCAT, but mass is still the same, 52.9 grams. What is the C value? Thank you, 2.02 joules per gram degree C, because that's our steam, which is a little different than liquid water. It's got a different C value. And then 130 is what you guys just told me for our temperature. So when you're ready, I heard 13,000. 0.5. Okay, I don't have room for a 4, so 5 joules. Got it. Okay, almost all the work is done, people. So we got every Q possible. But what was the question? How much heat? And it doesn't say summative, but it's summative heat. It's all these Q's added together. So let's add these together. But before we move on, do you guys want to stick with joules or kilojoules here? We can't do both. Kilojoules, okay. How many kilojoules is this one?
There's more joules than there's 3 joules.
Okay, there's 3 joules. Okay, I see your logic. This how many joules? Are you multiplying by 1,000 or dividing by 1,000? There's a lot more joules in a kilojoule, right? So you're going to have a lot more joules here. 17.6 is going to go to 17,600. You're killing me. Okay, joules. And then the other one is going to be what? 117,310. Yeah. Joules. Okay, so what you do is add those up, and that'll be your final answer. Woo, doggies. Okay. Let's talk about what we can practice now. Because it really depends on how well you do with these 3 and what I tell you to do after this. So on your practice sheet, go ahead and work on number 2 of the first section. So the little top right underneath the title there. So work on number 2 there. Number 2 on the next one. Can you start? Yeah, do 2, 2, 2. Let's see what happens. Let's see how this goes. Now, I did number 3 here, just FYI, okay? Number 3 was a beast. Please do not go in beast mode on everything. You need to read the question and see if you require a huge heat curve going from a low temperature to a high temperature. If it's not a big temperature change, just go with Q's equal to moles times delta H for your vaporization curve. So do 2, 2, 2 for me. And I'm telling you, you need the specific heat capacity of iron. I believe. That's the value you're going to need. That's the first number 2. I'm thinking no more than 6 minutes, about 2 minutes a question. And if we feel good, then I'll tell you what to do from there. Don't worry. That's a dust here.